Alright, so in this video I'm gonna be explaining another important article about domain adaptation. And so the name of the article is Overcoming Catastrophic Forgetting. We know this term from continual learning. I have a playlist for continual learning that I explain catastrophic forgetting, but we are overcoming it during domain adaptation of sequence-to-sequence language generation. So this paper is in 2022. Sequence-to-sequence language generation models that are trained offline with multiple domains in a sequential fashion often suffer from catastrophic forgetting. Lifelong learning, or we call it continual learning instead of lifelong, has been proposed to handle this problem. However, existing work such as experience replay, this is another technique in continual learning, or even this technique, elastic weighted consolidation. These are techniques that we do in continual learning, but these techniques require incremental memory space. And it's very natural that we have this problem of incremental memory space, because if you think about everything at the IID, then you should memorize everything. There is no structure in distribution of your data. So that's why domain adaptation is very natural. So in this work they propose an innovative framework, they call it this one, that leverages a recall optimization mechanism to selectively memorize important parameters of previous task via the regularization, and uses domain drift estimation algorithm to compensate for a drift between different domains in the embedding space. These designs enable the model to be trained on the current task while keeping the memory of previous tasks and avoid much additional data storage. So this can be combined with existing lifelong learning approaches. So this is the illustration of domain shift. Data with 3 relevant topic or cluster in the embedding space after model train on task 1. Or in B, you see data with previous topics in the embedding space after the model train on task 2. So this is an overview of the sequence-to-sequence language generation. So we have mean shift here to have domain shift estimation, which is necessary to create this shift vector array. But the model time t and model embedding t-1 embedding t, then these are important samples that we need for domain shift estimation. Because now we model training with regularized memory recall. So in this section, we introduce our proposed framework. It's a combination of regularization and domain shift estimation. So for the first part, we incorporate the mechanism of elastic weight consolidation to obtain a regularized memory recall mechanism. For a second part, which is domain shift estimation, we design an algorithm to integrate both the k-means and mean shift. A shift of embedding a representation is estimated using the previous and current models, and it is compensated to reduce forgetting when we evaluate the current model on test data from the previous domain. So although elastic weight consolidation is generic enough to fit all tasks, it regularizes all the parameters to the same extent. In order to differentiate parameter importance, we propose an improved elastic weight consolidation, the regularized memory recall mechanism, where the training objective is this loss, where L is the loss for the current task. In our generation task, we use standard label smooth across entropy. In the regularization part, theta star represents the parameters from earlier models that learned from task T-1. So theta stands for the current model parameters. And indexes I and j, this I and j here, are used to represent connections between pairs of neurons n sub I and n sub j. So adding the regularization term using differences between the two models is expected to memorize important old parameters while updating current parameters. So we don't want the parameter to move from the current parameters that much. So in elastic weight consolidation, this F is the diagonal element of the Fisher information matrix. It measures the importance of theta after being updated with a set of data points. I've explained this Fisher in the context of continual learning in my playlist for continual learning. However, in our work, we suppose that we do not have access to previous tasks. Therefore, we cannot compute fine-grained values based on data and thus convert F to a tunable hyperparameter without dependency on data. So it is used to penalize this quadratic function that we see here. So in order to make the parameters in a reasonable range, we add hyperparameter gamma to help tune F. And to control learning between loss for current task and regularization, we add this lambda of tau, which tau refers to update the time steps during fine tuning. So we integrate this for the fine-grained regularization, and this G here is just the gradient of the learned generative function. It could be transformer, it could be LSTM, or variational autoencoder. So we take the gradient with respect to parameter theta sub ij. Now we are talking about deploying domain shift to make up domain shift estimation to make up semantic drift. So catastrophic forgetting is mainly due to domain shift in the embedding space after the model is updated on the new domains. So when testing on previous domains, the embeddings derived from the model training using new domains are suboptimal and lead to performance degradation. Hence, in addition to regularizing the model during training, as described in the section above, we propose to deploy domain shift estimation to compensate the embedding drift to further reduce the forgetting. Note that in our lifelong learning scenario, we do not rely on the data previously used for model training in the new domains, but do have access to the trained model from the previous task. So we approximate this domain shift estimation with gaps between embedding representation of the current data based on the model of T-1 and T. So first, for a data point I in the current training task, its representation shift is here. Because these Z, they refer to the embedding of point I based on model T and T minus 1. So in the sequence-to-sequence language, these are encoder outputs. Second, we deploy unsupervised clustering methods to identify some centers and mean shift for the embedding using model T minus 1, especially with k-means. Instead of k-means, they could use, for example, mixture of Gaussians, which is more powerful, although computational complexity of them is pretty high. We find k embedding centers, each of them represented as mu. Then around each center, we find some number of samples to compute the mean shift. The mean shift for each data point of each cluster is this one. And G here is the Gaussian kernel. H here is the bandwidth. X sub I here is the data belongs to, for example, cluster X, because X could be your cluster. So N is the number of data points in each cluster. So finally, for each cluster, we computed domain shift vector. So this is what we need, this domain shift vector. A summarization is performed over all data points belonging to the cluster K. We use K such vectors as domain shift estimation between the model trained for two different domains. When evaluating on a previous domain using the model trained for a new domain for a test data point, we first calculate the similarity between its embedding encoded by model T and stored cluster centers, and then corresponding domain shift vector for the cluster is subtracted from E. So we can perform a series of subtractions, because each of these delta, all of them are domain shift vectors that are calculated here. So this algorithm, first we get the embeddings of training data of task T by model T minus 1 and model T, given function shift and Euclidean distance. But the aim of this algorithm, the output, is the estimated domain shift. So we get that delta that we need using the equations that I explained. And these are experiments. We compare our approach with the following baselines. The first baseline is fine-tuned for each task. Each model is initialized with the model until the last test. Or the full one, we train a model with all three data sets. Or elastic weight consolidation, which is trained with the based elastic weight consolidation model on the training data from the current task with the initialization of previous model. So these are examples of generated paraphrases by Bart's model or this data setting. On QTW is a data setting. And you see the domain statistics for this data, intent statistics for this data. And this is the average performance of continual learning, 6 domains. We have 6 domains.